suppose this vector field over here models a body of water. If I were to ask you, what's the net flow of water within a circle of radius 4, I mean, you could do all this calculus, but there has to be an easier way, right? And there is, the divergence theorem. Wait, what is a vector field? A vector field, modeled by a vector-valued function, is a function that takes a point as an input, and its output is a vector that starts at that point and has components that are in terms of x and y. Okay, and then what about this whole flow stuff? So at a point, the net flow is defined by the divergence, which is the difference between the outflow and the inflow. Now that we have a basic understanding of divergence in vector fields intuitively, let's take a look at some real-world examples.
Take, for example, this closed funnel. There's no water coming in or out, and so the divergence is 0. Here, there's a hose attached to the bottom of the funnel, and so there's more water coming out, and the divergence is positive. Here, the funnel is left open, and the water disappears into the center of the funnel, and so the divergence is negative. That brings us to the divergence theorem, which basically states that the total divergence of an area, shown by the integral over the area, is equivalent to the amount of stuff that goes through its boundary, or the flux. Let's try solving the problem at the start of this video. So now we know we just have to focus on the boundary. And so for every vector going across the boundary into the circle, there's an equal vector going across the boundary out of the circle. Those cancel, and the total divergence is 0.
If you're anything like my mom, you're probably thinking, this is useless. But trust me, vector fields are everywhere. In fluid dynamics, electricity, magnetism, even weather and climate, vector fields play an important role in shaping the world we know. Thanks for watching, and don't forget, if there's anything that MRI machines, hurricanes, and magnets have in common, it's vector fields.